Welcome. Today's lesson we are talking about improper integrals with infinite discontinuities. So we have three scenarios we're going to go through today. So the first one is if we are continuous on some interval except at the upper bound. So if we're discontinuous at point B, what we're going to do with our integral is we are going to replace B with some variable C, and then we're going to take the limit as C approaches B from the left. Same thing if we have our lower limit is where we're discontinuous, then we're going to replace that lower limit with a variable C, and we're going to take the limit as C approaches A from the right. Now, if we have a point in the middle, right, there's some C inside our interval, which has a discontinuity, then what we're going to do is we're going to go ahead and split our integral into two separate integrals at C, and then we can go ahead and use rules 1 and 2 on each of those integrals respectively. A reminder that we say that these converge if the limits exist and diverge if the limits do not exist. All right, so let's try some examples. So our first one here, we want to evaluate the integral from 0 to 1 of 1 over cube root of x dx. So I'm just going to rewrite this from 0 to 1, x to the negative 1/3 dx, just to kind of help myself. And so when we look at this, our limit or our function, the cube root 1 over the cube root of x, is discontinuous at 0. So I'm going to go ahead and then replace that. And it doesn't matter what variable you use. I'm going to say b. And since it's the lower limit, I'm going to replace it with b from the right, as b approaches 0 from the right. And then b to 1, and then x to the negative 1/3 dx. And so then when I go ahead and take the antiderivative of that, I still have the limit as b approaches 0 from the right. And I'm going to get x to the 2/3 divided by 2/3 evaluated at b and 1. So then we get the limit as b approaches 0 from the right. And let's see, we have a 3/2 here. And then I'm going to go ahead and plug in my bounds. So if I plug in 1, I get 1 minus, and then b to the 2/3. And if I look at that limit as that goes to 0, as b goes to 0, this piece is also going to go to 0. So my final answer here would just be 3/2. So if I look at my function here, we can see that we have that discontinuity at x equals 0. And the area under the curve here would be 3/2. Our next example. Here we're talking about an improper integral, and this one is going to diverge. So let's see what that looks like. So I'm just going to rewrite this with my limit because 1 over x cubed is discontinuous at 0, has infinite discontinuity. So I'm going to take the limit as b approaches 0 from the right again, from b to 2. And then I'm going to rewrite it as x to the negative 3, just because that's how my mind works when I talk about antiderivatives. So then I'm going to take that antiderivative. And so we have x to the negative 2 divided by negative 2 evaluated from b to 2. And rewrite that. So I have negative 1/2 over x squared. So limit as b approaches 0 from the right to b. And when I plug in my bounds here, I'm going to get the limit as b approaches 0 from the right. And then plug in the 2, I'm going to get 2, so negative 1/2 or 1/8. And then plus 1 over 2b squared. Looking as that goes to 0. And as my denominator there, we're thinking about as we're approaching it from the right, getting smaller and smaller. So this piece actually is going to infinity. So then I get negative 1/8 plus infinity. So this whole limit goes to infinity. Therefore, it diverges. Okay, and the little triangle means therefore. So if you'd like to start using those 3 dots in that triangle form to say therefore, you are welcome to. All right, our next example. So here we have an improper integral with an interior discontinuity. So we have the same integral we just did, so except our bounds are different. So now our bounds are from -1 to 2, but we're still looking at 1 over x cubed. And so our discontinuity here happens at 0. So what I would do is I would split that up into -1 to 0 dx over x cubed plus, and then I would go from 0 to 2 dx over x cubed. And then what you would do is you would go through and you could set up your limits. So I could set this up as the limit as I don't know, however you want to do it. You can do it a couple different ways. But you have to pick 2 different variables here because we want to make sure that we're not using the same variable for both bounds. So if I pick b from 0 on the left-hand side here, from -1 to b, then I'm going to make sure I pick c on my other one. And we already know that this diverges since our last example told us that this one diverges. Okay, so it diverges, okay, by the last example. So if either of those integrals diverge, then we say the whole thing does. All right. And then our last example here talks about if we have a double improper integral. So here we have a discontinuity in between. So we have a discontinuity at 1, and we also have, or sorry, not at 1. We have a discontinuity at 0, and we have a discontinuity at infinity. Okay, so what we're going to do here is we are going to go ahead and split it up so I don't have to have 2 limits within one. And you can pick any point between 0 and infinity to split it up. So I'm going to pick 1. So I'm going to go from 0 to 1. And then my other integral will go from 1 to infinity. And so then that allows me to do my limits differently. So on my first limit here, I'm going to approach 0 from the right. And then on my second limit here, I'm going to pick a new variable, so c, and c is going to approach infinity. And that's from the last lesson. Okay, so now that I have my limit set up, I can go ahead and take these integrals. And so what I'm going to do is I'm going to actually do some u substitution here. And so if I let u equal the square root of x, then du dx is going to equal 1/2 x to the -1/2, which means that dx is going to equal 2 square root of x du. And so how that's going to help me is because now when I replace dx with 2 square root of x, it's going to cancel with that other square root. So then I'm going to have the limit as b approaches, but I'm not going to change my bounds here. So I'm going to leave this as x equals b and x equals 1. And I'm going to leave this first square root, but I'm going to change x to being u squared, right? Because if u equals square root of x, x is u squared. And you'll see why that's helpful in a second. And then I have 2 square root of x du. And then the same thing over here. Oops, I forgot my limit notation. Forgot my x's. Okay, so then my square roots will cancel, and I have a 2 now. And then I can see that 1 over u squared plus 1 is actually a formula for arctan. So that's where this u substitution comes in helpful, because it allows me to see that I actually have an arctan antiderivative here. So I have 2 times arctan. So, and then that's going to be, so I have the limit as b approaches 0 from the right, and then I have 2 arctan, and then arctan of u, which is the square root of x. Oh, sorry about that. From b to 1, I switched everything back to x. And then same thing over here. So limit as c approaches infinity now of 2 arctan square root of x from 1 to infinity. I don't need to write the x equals because everything is back in terms of x. So then when I plug in my bounds, so arctan, remember, I always have to think about arctan a little bit. Arctan is the function that goes like this, and where my upper limit is pi over 2 and my lower limit is negative pi over 2. So then I have the limit as b approaches 0 from the right of 2 arctan of 1 minus 2 arctan of the square root of b, plus the limit as c approaches infinity of 2 arctan of the square root of c. I wrote infinity. These should be c's. Dang it. Okay, typo. I'm doing it in a different color so you can see what my typo is. Let's see. When did I start? There we go. Okay. Great. And there's my typo. So arctan of c minus 2 arctan of 1. So which angle has a tangent of 1? That would be pi over 4. Sorry, I'm dropping my stuff here. So then I get 2 pi over 4 minus, and then the arctan of 0 is 0, so 2 times 0. So that's my first one. And then over here, once again, 2, and then if I look as c approaches infinity, I can look at that function and see that the upper bound would be pi over 2. And then minus 2 arctan of 1, we've already decided was pi over 4. So then this goes away at 0. These cancel out, and my 2's cancel. So my answer here is just pi. So that means if I look at this function over here, this area of this function under the curve, if I start at 0, it means that this area up here and this area down here become so insignificant that I can actually sum it all up and get pi. All right, that's the lesson for today. Go ahead and try the homework problems, and I will see you in class.